Hi everyone, welcome to another episode of the Haskell Study Group. I'm your host Ram Vedam with Atlanta Functional Programming. I hope you all are having a good 4th of July if you're in United States. Those of you who are watching internationally, I hope you guys are enjoying your Sunday. Today we're going to be discussing the topic of recursion inside Haskell. This covers Chapter 8 in the Haskell book. If you're following us and following along with our discussions through Learn You a Haskell, this topic is actually covered in Chapter 6, I believe. Chapter 5 of the Learn You a Haskell book. Recursion is a common topic that's kind of discussed in functional languages, primarily because it's often used to implement various types of iteration inside functional languages. It's a technique that basically comes from mathematics, as many of you know, where you are actually defining an expression with respect to itself in a so-called self-referential manner. Since Haskell is considered to be, and for most part still is, implementation application of the lambda calculus, there's no technically a notion of recursion per se inside Haskell. Okay, this is something that's a little surprising to most folks when they start understanding the theory behind Haskell, but it is something to be said. And that's because the lambda calculus itself does not appear to have any means of recursion, because when we're talking about lambda calculus, oftentimes we're talking about lambda expressions, and since lambda expressions are anonymous, you can't refer something without a name. Okay. Being able to write, though, recursive functions with respect to names, though, is essential, at least when you're talking about the Turing completeness of a programming language. Luckily, for lambda calculus, there's a technique that you can use to write recursive functions inside of this, still maintaining the anonymity feature of lambda expressions, and that is called the combinator. There are many types of combinators. We won't cover most of them. I introduced some of these early on inside some previous episodes, but it is a topic that is necessary to be aware of. It is a fairly big topic, actually. There are several books on combinators, but to understand recursion inside Haskell, you have to at least understand one of the basic combinators, known as the Y combinator or the fixed point combinator. Now, I won't cover the depths necessarily, and I don't think the chapter itself covers the depths of the Y combinator itself, because the Y combinator and breaking down the Y combinator does take a little bit to understand. So we're going to kind of focus on some of the techniques to actually implement recursive functions inside Haskell, but we will we'll delay and approach the deep dive of the Y combinator itself at the appropriate time. For now, just know that when you are writing recursive functions inside Haskell, you are essentially writing a version of the Y combinator. You are adopting and applying the Y combinator to the definition of your Haskell function. It is very important to understand recursive functions, but it might often be the case that you may not write a lot of them, because a lot of the standard library in Prelude has higher order functions that have built-in recursion. And because of their recursive nature, you might see some behavior that you may not have accounted for when you were developing your Haskell programs. So by understanding recursion itself and how it kind of works, what we're ultimately enabling ourselves to do is to understand that the design and how a lot of these higher order functions inside Haskell are implemented. So that's what we're going to be covering today. We're going to be kind of talking about what Haskell does with respect to implementing recursion, and how we might go through and write our own recursive function for the sake of understanding how to implement them using Haskell's features. And then finally, there is a particular feature inside Haskell that would prevent infinite recursion, um, and won't for especially for computations that may not necessarily successfully result in a value. Um, if that happens, then of course, if you write functions that might blow up the stack, um, you want to be able to, at least inside Haskell, inside the REPL, to be able to stop the function without necessarily have to stop the entire Haskell REPL itself for that current session. Okay, and that feature is called bottom, and we'll go and take a look at that and see what exactly bottom does when we start writing our own examples of recursion that doesn't necessarily stop. As I mentioned, recursive functions inside Haskell are just, standard functions that are self-referential. They are, this is what recursive functions are in general. And what happens is they, for folks who, just a review, the notion of recursion comes from a natural property from both mathematics and actually going even further to logic. Now, yes, there is logic in mathematics, mathematical logic. The logic itself is its own branch of philosophy, so you need to keep them technically separately to be aware of what that is. All right. Mainly, recursion is allows you to concisely define a potential algorithm, okay, or solution to a problem in terms of itself, in terms of the actual function, in terms of the recursive function itself, okay, to allow for specifically, and let me just go to this, to allow for specifically the ability that enables the ability to take a potential infinite number of steps. Okay. Or indefinite is probably the more appropriate term here. All right, indefinite number of steps to return that particular result, to compute that result. Okay. And that's something to be aware of and something to be very careful about, just because of the fact that what this is telling you is recursive itself has a finite bound, but that bound may not necessarily be known. We only know that, the end point, which is our base case. Um, and that is the stopping point at which all other computations will then suddenly trigger and compute the final result. Okay. But that might potentially take a long time, depending upon the size of the recursion and recursive depth of the actual call, and that could be found out through measuring and all this kind of stuff. But it is something to be aware of when you are you know defining and actually implementing recursion. One classical example that you could use to implement recursion is, and we're going to use this to talk about recursion, is two things, okay, and that is two specific classical examples of recursive functions. One is the Fibonacci function, and the other is factorial. All right, we're going to begin with factorial just for the sake of not enabling us to use particular particular techniques to actually go and implement functions using, like, say, if-else expressions, because of course you could certainly, leverage those. But one way to write recursive functions, actually one of the best practices to write recursive functions inside Haskell, is to use the pattern matching feature that's available in Haskell. Now, we've encountered the pattern matching feature already a couple of times when we were defining our functions, but we never really used it for this particular type of case. And now we're going to probably we're going to start diving into the specific case of how to define recursive functions using this pattern matching capability. All right. So, quick review for folks who don't remember factorial. All right. Factorial is nothing more than essentially the function f of n equals n factorial, which is equal to n times n minus 1 times all the way to 1. Okay, so it's essentially multiplying everything up to 1. It's a product of all the numbers between the upper bound, which is n, and the lower bound, which is 1. Okay. So if you use an example, it's like, say, 4 factorial, it's going to be 4 times 3 times 2 times 1, which is 24. Okay? To define this function, we could simply just, implement a function that just computes, this particular value. Okay. Obviously, if we define, say, 4 factorial, this example is from, referred in chapter 8. If we go through this is a silly way of doing this, but this is just essentially a constant that actually computing and doing computation, evaluation of the function. The evaluation of the expression 4 times 3 times 2 times 1 to give us our final, value, which is 24. Okay, but obviously this structure, writing it for all n, not only is impossible given the fact that the natural numbers is a countably infinite set, but also you have to realize that this function accordingly doesn't actually encourage code reuse, okay, because this is essentially just a constant, right? So we could rewrite this, and everyone knows that we can rewrite this by just simply, writing a function that takes in an integer and returns an integer, or, and because since we're dealing with non-negative integers, really, we could even go even further than this, but we'll take integers for right now to have a stopgap. And we'll just define the function with n with a particular things like, let's say we define it as factorial of n minus 1. All right. Obviously, anybody who's looking at this will realize this is, let me do this, actually, it's n times factorial of n minus 1. And obviously anybody who reads this will know that this is currently giving us the recursive structure, but we don't have, this will not stop. If we actually run this, we'll end up having it go through and blow up. It will actually just obviously sit there. All right. And I just, geez. 1 second. I accidentally should not have done that. Go back. Let's see. It's infinitely recursing. 1 second here. I probably have to kill Emacs. Okay. Brief problem. 1 second here. Let's do this again. Okay. My apologies for folks. Let me do this one more time. Okay. And do this. And go back to this. And switch it to okay. My apologies, I had to restart the Haskell REPL. Okay, so let me go to 4, to Recursion, and let's, so we just saw that what happens is obviously this is going to blow up the stack and go in an infinite loop, and you'll have this one issue. Now, for folks who are wondering why bottom didn't actually go and execute that, we're going to touch base in this, but just in a bit. But just to give you a quick answer for it, it's because of the fact that we didn't actually explicitly provide a case where bottom is actually going to occur. But in the case of this infinite thing, this is just because we didn't actually provide a base case, right? Now, if you remember a couple of, I think it was last week when we were talking about functions, especially for pattern matching, what happens is it's going to find it's going to go in a sequential order and find the first pattern that actually fits and then execute that pattern. Now, in the case of Factorial, or any function that's taking a single example that has a base case, this means that you want to actually put your base cases in order inside your actual file that you're editing. All right. Otherwise, what ends up happening is you're going to always end up hitting this case. And you're back to infinite recursion. So you can't necessarily put this here expecting Haskell to actually recognize that the factorial 0 equals 1 is the first base case, because it's going to go in the order in which it registers those patterns in order for those patterns to actually be executed. Okay. Now that we have this, we can totally go ahead and now call for a factorial function on 4, and you'll see that we'll get our 24. Okay. What this is illustrating is again, factorial is essentially, I mean, and we can go through this. It uses the pattern matching feature of Haskell for function definition to actually go and define a recursive structure that then at evaluation time, when it's doing function application, it'll go in and search through these rules to provide the correct rule, and then that's what ultimately determines the next stage of the function application. So if we actually look at this first function in the case of 4, if we want to do the 4 factorial evaluation of above function, what it will first start out is it will start out as 4 times factorial of 4 minus 1. Okay. The reason for this should be pretty obvious. When we call for, we're going to do a lookup on the rules provided for factorial. We recognize that factorial n is the rule that best matches the given argument that's provided, and then we go ahead and use that for the function evaluation. And we keep going through this evaluation, okay? So we aren't necessarily done yet. It recognizes it can't technically evaluate the expression yet, so it goes through another stage and recognizes that this is evaluated to factorial 3, so it'll go ahead and says, okay, this is 3 times factorial 3 minus 1, and we'll compute the 3 minus 1 immediately on the next stage, makes that 2, and then we'll go over and do 3 times 2 times factorial 2 minus 1, and then, of course, we go through and say 3 times 2 times factorial, right, times 1 times factorial 1 minus 1. At this point, factorial of 1 minus 1 is obviously factorial 0. It's going to recognize the fact that factorial 0 has been hit. It's going to return 1, and then we can certainly do 4 times 3 times 2 times 1 times 1. Now that we have the expression completely evaluated, we can now go through the process of computation and complete the evaluation phase, and we can actually compute 4 times 3 times 2 times 1 times 1, which is an expression that will then result into our final answer, which is 24. Okay, that's how the pattern matching necessarily it works, and it will certainly be the one that ends up being useful for you that you'll end up using often when you are writing your code. Another way of writing this, actually, though, is something that we've seen before too, and that is, and I'm going to call this my factorial, and that is using guards. You can actually use guards to actually go and do this as well. So you could do this, and then you write, you do this and say if n is less than 1, you provide 1, and otherwise n times factorial and minus, sorry, not factorial, my apologies, my factorial, and actually it's, I have to write I think I can actually write it this way, and we can also use the where clause if this doesn't work. This should also be the same thing. So if we go and type in my factorial 4, you can see that it's also 24. So you have two different ways actually to write this recursive structure. Which one is more appropriate is entirely based on what it is you're attempting. But guards is another way of also adopting and implementing your recursive functions. Okay. If you want to really think about what recursion is at a higher level, we can look at recursion as another way as being essentially a self-referential function composition. Okay, so if you remember function composition, we have essentially two functions, f and g. Okay, and if we wanted to compose f dot g using the dot operator inside Haskell, this is equivalent to f and let me just write this more correctly, f dot g of x. This is essentially f of g of x. Okay, so what's happening is it will recognize that the argument is coming in, and it does a right to left application of the functions provided, taking the rightmost function applied to the argument, taking that result and taking it percolating its result up to the next function that needs to be evaluated. So in this case, it will go from G to F, and then the result of G will be the input of F, and then we'll have, as a result, the F of G of X as being what is evaluated. Okay. Now, this pattern matching feature that we see here cannot be understated as being a very, very important piece to the puzzle. And you can see that it's going to be the basis for a lot of stuff that we are going to be encountering later in this chapter. So please take a note of this. All right. With respect to the recursion is self-referential composition, there is a reason why this is important to know, and that is in Haskell specifically, there is a function that because Haskell again is built purely on the lambda calculus. There's only one function for expressing these kinds of computations that can be evaluated, and that is coming from from apply. So that is the verb that is used for expressing computations that are going to be evaluated. We apply a function to a specific argument, and applying that function to an argument returns a result. And that result is then going to be used as the input for another function that's going to be coming into play. The same idea can be applied in and can be seen when we start illustrating some of the code with some different, some basic examples. Okay, take for example, just writing our own increment function. Okay, so if we write our A that takes an A and returns an A. Okay, we put in obviously the restriction that the A has to be some numeric type class. Okay, and our increment is going to literally just be equal to, let's call them +1. All right. Remember, this is partial function application. It's returning us a function that takes in one argument. Okay. If we want to calculate certain types of functions, we could certainly, calculate certain types of values as constants. We could certainly call this increment function, okay, just through pure function composition, all right, and pass in our input value as our starting point to ultimately compute the final constant. So in the case of 3, we can just go ahead and compose a function that is really just increment called 3 times, and again, it's technically referring to itself, and then we pass in has the input argument 0, and this ultimately, oops, did I forget something here? Oh, hold on, I may have messed something up here. My apologies. Okay, and if we call this function, you can see that this is just 3. All right. Another way of actually defining this, and again, this here obviously is because I didn't specify that this is an integer. Let's, another way of actually creating this, again, this is going to be an integer, is going to be also just this guy, really, applied. Instead of using the arguments, you could just certainly do this, and you'd have the same function, all right? So this will give us 3 prime, and this is 3. All right. Both of these are actually equivalent, and if you recall, the dollar operator is one that just allows us to get rid of the parentheses and make it easier for us to pass in functions and make things like function composition a little bit more readable than having nested levels of parentheses for something that ultimately is just returning a function. But we might want, in this kind of function, something that's going to be some starting point, and we want to be able to, increment a particular value an indefinite number of times. Okay, some finite number of times specified as an argument. Okay. The way you would do that is by defining another recursive function. Okay. Again, this is nothing more than us actually defining what we did with Factorial. Okay. We could define a function that just says, okay, and this I'm going to refer to. This is in chapter 8 of the Haskell book. Because I thought this was a good example to go through. This example basically takes in a function, okay, that has an argument that has to have an equal, that needs to adhere to the equality type class as well as being numeric, and it's going to just return us a function that takes 2 arguments in turn, returns an argument of n. And this function, what this does is it's going to have a base case. Obviously, if we're going to be already at the upper bound, then obviously we don't need to increment anymore. So we just need to say, okay, this is just going to be n. Okay. But other than that, but we could have actually something that takes in something that we want to increment certain times and the n value, and what we'll get is 1 plus inc times that, times minus 1. We're decrementing the number of more times that we have to run this function, and we go to n. Okay, and what this function does is if we call, for example, inc times, okay, and we do 10, 0, okay, we'll get 10. If we do inc times 10, 1, we'll get 11. If we do inc times, 5, 0, we get 5. You can see very quickly what's happening is that this is just nothing more than a counter that from some starting point that will return us the last value of it being evaluated. The main thing to learn from this is really the structure of how the recursion is actually happening here, okay? That's particularly important because of the fact that that is often what you're going to end up using, all right? But this itself has a lot of stuff that we could technically abstract, okay? If we think about what this is ultimately doing is, this is applying a function, addition, to some starting point, okay? And it's specifically applying addition of 1, so it's applying a partially applied function that's an increment function a certain number of times to some starting point, okay? We could actually go ahead and extract this and make this an algorithm that can be then just equally used to apply, create a function that could take any function and apply that function multiple times to a single argument. All right, I'll give you the name of this function in the Haskell book is called apply times. Okay, and what this function does is the same thing that we saw here. We just go ahead and apply it, and what we do is we take in an argument. Okay, that's the number of times that function is going to be called. We're going to take in a function that takes in an argument and returns an argument. Okay, And what we're now doing is we're going to return a function that takes in a single argument and then returns that argument. Okay. This piece here, you may have noticed, is using a different type variable, and the reason for it is because of the fact that it doesn't necessarily have to be the same type that when you're generating that second function. Okay. That's something that is not required. Okay. Given this definition, what is our base cases? What is our recursive case? Okay, this is something that obviously we need to recognize. Okay, the base case is still the same. Okay, we want to stop when we no longer have to iterate, and since our first argument is going to be our times, our counter variable, all right, when this first argument turns to 0 and we hit B, okay, we're just returning B. Okay, we don't need to return anything else. All right, but if we're actually going to be still in a non-negative number, all right, if we're not done yet, then what we want to do is we want to apply the function f to apply times n minus 1 fb. Okay, why is it apply times of n minus 1 fb? Well, it's because we're trying to essentially apply the operator, as we saw here, to the result that the recursive call that's actually being provided, as is indicated by this piece here. So this f of thing, think of it as just a function application. This is just the expansion of this, all right? With this function, what we can now do is we can now define increment times the same way with a new, much more simpler function structure, all right? So we have our same signature, takes two arguments and returns an argument. Okay. Then what we do is we call increment times. We call times as our non-function, and what we'll do is we'll just apply n number of times the +1 function on n. Okay, and if we look at this, inc times prime on 10 and 1, we'll end up getting the same evaluation function. Okay, this refactoring, starting from a specific case to something that's more general, is going to be a pattern that you're going to be using heavily when you're writing your Haskell programs. Because you want to start with the base case to allow the structure to come out, to fall out from examples, and you'll end up coming up with very specific, very clean generic algorithms that can be applied to multiple places when you're applying those structures. All right. So just take note of this and be aware that this is something that you need to be you can account for. And I just realized that I don't really need this piece here because of the warning. That doesn't actually change anything. See that the function is the same. So bottom in Haskell, as I mentioned earlier, refers to computations that essentially fail. Well, they're not necessarily failing. They just don't successfully return a result, a value result. All right. There are two different types of bottom computations. One, again, is an error failure, real, and another one is what I was talking about when I was talking about recursive functions. You're infinitely recursing. Bottom itself comes from mathematical logic and from logic itself, and it corresponds to false, right? You can see that it will be the case that what bottom is when you run a function that refers to itself, that is never going to actually return a result. in the simplest example is just referring a variable inside of an expression and have no bottom things. All right. If you write something like this, and this is actually going to loop forever. All right. Now, for some reason, it looks like the best way to really illustrate this is in GHCI proper, because it looks like Emacs and Dante is kind of messing with my demo here. So let me just go into set up this and give you guys a better approach to this. 1 second here. Here. And so to show this, I'm going to go ahead and switch to a different application here. I'm going to switch to a real Haskell session or Haskell REPL. This is obviously the stack REPL. Just taking a little second here to let it switch over to our REPL here in the stream. Okay, so X and X. You can see that this is interesting. This is not throwing actually an error at all. That's kind of weird. So it looks like they may have there might be an issue in GHCI because GHCI normally should be throwing on Linux and Mac an exception here because it short circuits the computation. That's an example of bottom recognizing the structure being able to be fixed. But there was an issue with Windows that it looks like got thrown back into Mac and Linux too, because now it looks like what's happening is it's consistent in the fact that it's just going to never end. It's just going to freeze GHCI until you actually go in and interrupt the computation. It's just going to infinitely recurse. But GHCI has some guards to allow you to hit and throw such an exception when you hit a specific case. In the simplest example, we could write a function here. Actually, my apologies, I'm going to do something here. Let me go back to stack REPL. And okay, so now let's go and define a function that takes in a bool and returns an int. Okay. This is an example that's again inside chapter 8 of the Haskell book that I think is a pretty good example to go through. What we're doing is if we return true for something, we'll say error. All right, and if we return false on something, we just return 0. Okay. And we just go ahead and do that, and we defined our function. So if we go ahead and define f false, we get that. If we say f true, we end up throwing an error exception, and it'll throw a call stack for us. Okay. In the first, obviously, as with anything, this is using pattern matching. We got f false. It goes, looks up, figures out that f false is actually clearly defined, and then it returns 0 as a result. But it doesn't result in a bottom value. But f true, because we're actually explicitly throwing an exception, we are failing with error. And failing with error is actually interpreted by GHCI as another case of actually using bottom. It'll actually abort compilation and then throw you back to the prelude, which is what if you're using interactive development, this is kind of what you should be expecting. Another case of bottom, though, is what we encountered before, and that is the case where you are defining functions, but you didn't provide all the rules for that function, okay? So, for example, if we define, in the similar example, an f prime that takes a bool and an integer, okay, but we just said f equals false, okay? And we, this time, just call true, what we're going to end up getting is an exception that is thrown that says non-exhaustive patterns in f function f prime. Remember this non-exhaustive pattern as being the case where essentially it does a lookup, recognizes that there are no recognizable patterns for this given input, and then it just throws an exception to abort compilations instead of letting the REPL hang. This happens as well, and this is also an example of bottom too. You could fix this by using an otherwise clause too. But what happened is though is if we really examine the evaluation, the error clause that you're seeing inside of the terminal, that's actually Haskell adding a generic case for you, where it's like, I don't care what input you give me, there's just no rule for this input, so I'm just going to go ahead and abort the compilation. I'm just going to throw an error on everything else, right? So if you look at this, really what we've just defined earlier was something like this. Bool int f false equals 0, and then there's a new rule by Haskell that gets inserted by GHCI that essentially says error, and then it provides essentially a $sign here, and then it allows you to essentially write out your exceptions that you want to actually, provide. It injects, this exception ... sort of situation. All right, and I'm not going to write out the entire error message here, but you could think of this as being a string concatenation of this error message here that we're seeing, this non-exhaustive error message being structured and created by this final rule that's being injected by Haskell itself, right? Such a partial function is one that doesn't really handle all its inputs, as you can see. GHCI in Haskell itself as a whole prefers total functions that handle most of its inputs, right? And that's an issue that needs to be solved, right? How do we handle the case where we don't necessarily have something that will handle all of its inputs, okay? Well, to make such a function into what's called a total function, which handles all of its inputs, you have to use essentially the maybe type to actually go in and figure out whether or not you are actually going to return something or not. Okay, the maybe type, as you can, if you recall, is if I just do info maybe, it will give it to me. Yes, so the maybe type, if you recall, is a data type that's defined as being nothing or just a. So how do we define a current function that we just did and into something that makes maybe? Well, we have to first update the function signature, okay? This is very important. So we're going to make a new function called f double prime that is defined as a bool and returns an int. And what we're going to do is f double prime. Oh, sorry. I just did that wrong. Let me go and change that. F double prime bool, and instead of returning an int, we do a maybe int, and now we have our two base cases. F false is just 0, and f anything else is just going to be nothing. Okay. So now, if we call f false, we'll just say just 0 as we normally would, and if we call f true here, you're going to get nothing. Okay, and we've essentially now threw out the possibility of getting into that situation where we're going to go into the exceptional situations or the bottom situation due to the fact that we didn't have a rule defined for failing with error or something that doesn't return a result. Okay. This is important to provide because obviously that makes your functions total and allows the evaluation phase to actually complete itself. All right. If you don't provide something like that, then you end up having some issues. But note that we not only provided a brand new definition by using the maybe type, but we've actually encountered, okay, the case where you are returning a particular you had to change the rules so that the rule actually constructed that specific type. Okay, is there a way for us to encounter to change this slightly different to see some interesting errors? Well, we can. If we actually define this like I'm just going to go ahead and use boop f again here as maybe int, okay? And instead of defining f false to being just 0, we say 0, and then f anything else is going to be nothing, okay? What you're going to get is you're going to get this instance that the rule that we've defined is incorrect, which makes sense because obviously we can't actually construct the just construction from this integer from numeric, all right? So one way to fix this is you could write the following, maybe int, okay? And f false is 0. We're going to cast this as an integer, and f nothing equals nothing, and then we'll get another error message here, all right? you can see that what's happening is you can't just use a particular type constructor, that is the maybe type, and then assume your existing code is not going to end up having to change and construct it, because you have a new set of types here. Okay, we have to wrap the 0 in the function or the integer into a just type. Otherwise, the inferencer, all right, when it's actually constructing that function, it's going to recognize that there are rules that their types don't necessarily match the function signature, and it's going to throw up an error. All right, this is the beauty of the actual the Haskell type checker. Okay, cannot be understated that you can't just simply change the function signature and just expect everything to work. You're going to have to also change the rules on how you are constructing those functions, right? And this is because we're getting all these type errors. So let's correct this again. So this is bool maybe int at false equals just 0, and everything else equals nothing. And now we have our f true being nothing and f false being just 0. So another example, as I talked about before, that we should really review for recursive functions is the Fibonacci function. All right, this is another classical function that we everyone knows, but it's a function that we can use to actually determine how to write a recursive function inside Haskell. All right. The first thing to do when you're thinking about recursive functions and defining your recursive functions is to consider the type signature in which you're going to define them. Okay. I think this would be best illustrated if I switch back to Emacs here. Give me just 1 second. And go back to and let's do this. All right. So when we're going to define our Fibonacci number function here, now we'll go ahead. The first step is to consider the type signatures. Okay. The types, and this is important because again, this is going to be related to the type signature that we're going to be writing our function. Okay. In the case of the Fibonacci numbers, you know that the numbers that you're going to be dealing with are restricted to the integral types. All right, your small integers all the way up to big ints. Right. There's two ways based on this information that we can actually write the signature. Okay, we could because if we're looking for all integral types, that means we're not only dealing with int, we're also be dealing with integer and all the other related integral types that are available. Okay, so one might first say, well, int is basically subsumed by integer, so we could just go ahead and maybe write, Fibo integer, right? But, a more appropriate way of actually maybe writing this is, instead of using this, is to say, you know what, we have this type class called integral that we can use on the type variable, and if it's an integral type, which means int or integer, we could just go ahead and use this function, okay? And that actually is far more flexible, because now you could switch between either or, and the type checker will not be forced to actually just go and promote something that could be represented in a smaller number of bits. So knowing that and being able to say, okay, well, I can use smaller types whenever, and I can still use this, will really help you write generic type signatures, and more importantly, it allows you to get better practice with leveraging type classes where they are appropriate. Okay, so given this signature, we now have to consider how to write the actual function. All right, we have to first remember the base cases. Okay, inside our function. Okay, now consider base cases for the recursive function. And in here, we have to again recall what are the base cases for the Fibonacci sequence. Okay, this is pretty simple. You can write down the Fibonacci sequence. You'll recognize that the base cases are 0, 1, and then it will start the sequence there. It'll go 0, 1, 1, 2, 3, 5, 8, and so forth. Okay. So the first base case we need to obviously write then is Fibo 0 is going to be 0. Okay. The next case that we need to write is the second base case, which is 1. Okay. So if it's 0, we encounter that it's 0. If it's 1, we encounter it's 1. All right. Now we need to determine the recursive case. Okay. And in this case, we're going to have to consider the arguments to the actual function that's being passed in. We've already kind of thought about it because we know that the function requires that the arguments that's being passed in is an integral number. But the main thing is to realize that since this is going to be an argument, this isn't. We could just specify our third case, which is actually going ahead and implementing the recursive case. Okay. Now, systematically, you could just say in the book, and kind of the Haskell book kind of illustrates that you want to consider the arguments and then consider the recursion as two separate steps. Really, if you know that you are doing this in one step, I prefer that you just go ahead and recognize it as being this case and implement the recursion. Like the arguments on what's going to be done. Okay, and you know that the evaluation structure is going to be the application of this argument to this particular function level. All right. So what you're doing is ultimately you're determining, okay, what is actually going to be computed. Okay. So in here, what we're doing is we are actually computing x minus 1 minus x minus 2, but that's not exactly what we're doing. What we're doing is remember, we're actually making a call to Fibo to actually go and compute Fibo of x minus 1 and Fibo of x minus 2. All right, that's the actual recursive function. Okay, that's what he meant by actually, at least I understood how the recursive calls are actually going to be end up being created. Okay, so what you're doing is you're first determining the base cases, okay, and then you are determining what the recursive case is going to be, okay. And the recursive case is how are you calling the Fibonacci, the Fibo call, okay, function with respect to the incoming input, okay. In this case, we already know that in Fibonacci, if it's not 0 or 1, the next Fibonacci number is the sum of the two previous numbers, okay. So this is why it's 0, 1, 1, because 1 is 1 plus 0, and then it's 2 because 2 is 1 plus 1, and so forth, okay. You are essentially figuring out that you need to know the Fibonacci number, the two previous Fibonacci numbers, which is computed by x minus 1 and x minus 2. So what you're asking is can I have the two previous Fibonacci numbers, and then I can just go ahead and then sum them up. Okay. This systematic approach, yes, is a little tedious, if you will, when you're first starting out, and especially for newer programmers who are using Haskell as their first language to learn. This is going to get some getting used to, but the cost of that will be great. The final thing that we're going to be talking about, and this is something that we're going to be, it's going to take a little bit of, just structuring, is integral division. Okay, this is a topic that's in, section 8.5 of the Haskell book that I think is important for folks to look at. There's a comment. Yes, recursion allows the compiler to do all the work except in the terminal cases. That is correct. That's the beauty of recursion, right? That's why you don't necessarily need loops. You just need recursion, right? If you have recursion, you can actually do a lot of stuff. Loops allows you to hide recursive calls behind the scenes, but really you don't necessarily need loops in order to do iterations. But you will always need recursion and its capabilities inside of your compiler. But before we get into integral division, there's one thing that I wanted to mention. Yes. Up until now, and again, this is just going to give you a little bit more intuition for, in general, on how this can be structured for other types of data structures. We've been dealing mainly with integers, and we're going to be dealing with integers still with the integral division example finally. But before I do that, I want to actually let's finish off integral division, and then I'll touch up with this example, because I want to also cover the fact that you can write recursive functions with generic structures itself. So what is integral division? Integral division is basically nothing more than instead of obviously getting a real number, all right, an actual double or float for some calculations, you're going to only get the you're taking two integers and you're actually just dividing them and getting the quotient, not necessarily the quotient plus the remainder written in a floating point form. Okay, that's what integral division is about. If you know the types, you could certainly do something like this and write a signature for integral division. Okay. As being the function signature that takes in two integers, returns an integer, and this is just a type alias to div. Another way of doing this, because remember, div is already available for us to do integral division. If you remember what div does, it actually takes an integral type and then returns just the. But what you can also do is you can create type synonyms. These are essentially things that will essentially recognize what you're actually passing in. So this way you have an understanding of what these integers represent. And honestly, this technique will allow you to actually get clearer function signatures. Okay, if you actually represent some of this stuff. Okay. We could use type synonyms to actually go in and create aliases on top of each piece of this. Okay, so instead of writing this, we could also write, okay, type aliases using the type keyword. All right, we'll name one called the numerator, which is itself as an integer. Something called a denominator, which is itself as an integer, and then the quotient, okay, which itself is an integer. And we can use this information to write our type signature, which is essentially, we're going to take the numerator, which is the top of the fraction, all right, what we're actually dividing by, and then the denominator, and then we'll actually get the quotient of this variable. And this itself is going to actually also compile and give us the same signatures. Notice that the type keyword, which is it creates an alias on top of the type. It can be used. The type alias that was used can be used inside of type signatures to make it easier for humans, for maintenance programs to come in and look at type signatures. Okay. But we can actually go in and implement the actual recursive function when we're actually when we're starting to talk about what is actually going to be implemented. Right now, what we've done is we took a shortcut. We actually implemented integral division using div, but we're going to actually go through the process of how div kind of works to actually understand what's going on. Okay, again, this requires us to first determine, if you write, divide by 25, you'll end up getting 4. Right now, it already works, but you want you want to actually think about the base cases and the recursive case to actually determine what is the actual thing that we're actually returning on. All right. So how could we implement division, integral division? Okay, this way. Well, one way of actually implementing this is just using simple subtraction and then having a counter that keeps track of the number of times we've actually gone through and implemented the number of times we've actually went ahead and subtracted the denominator from the numerator. All right. So in this case, in this kind of technique, what you would end up returning is actually a tuple for the time being. This tuple is going to represent the quotient and the remainder, not actually just a quotient. Okay. So here we're going to create a divide by prime just to show you the difference. This one is going to take in our integral type. It's going to then take in two arguments, that's our numerator and our denominator, and then it's going to return a tuple of which represents our quotient and our remainder. And what we'll do is we're going to divide by this, and we're going to take our numerator and our denominator, and we're going to call a function that does our subtraction. All right. Let's call this function div compute. All right. The book itself calls it Go, but I'm just like, Go seems too generic, so I was just like, I'm just gonna say div compute or something like that. So we'll just compute div. Okay. And it takes the numerator and the denominator and some starting value. Okay, that starting value is basically the count, the starting count that we're going to actually go and use. Okay, this is going to be taking the numerator, the denominator, our initial count, and it equals the following. It's going to be a guard. Right? We're going to use guards to actually do this. And there's two cases. If we are less than the denominator, okay, if the current numerator is less than the denominator, we've computed the quotient is represented by the count, and the numerator is now representing the remainder. All right. If it's not that case, okay, what we're actually going to do is now we can actually subtract. Okay. Do this compute div, and we can subtract from the numerator the denominator. We're going to pass in the denominator because it's a constant in this entire calculation, and then we can increment the count to actually go and move into the next stage. All right. I may have messed something up here. Oh yeah, my apologies. I have to get rid of that. Thank you. Okay, there's a comment here. Okay. So there was a comment earlier about loops that I'm just going to read off here. Loops that terminate when x equals something are actually recursive calls, with the test being the edge case. Yes, that's a good way of looking at loops. Although that's actually how if you're coming from the scheme world and the tail recursive world, that's actually how you implement loops. I'm not mistaken. Yeah, I think so. The edge case is what ends up terminating it, but that's also a recursive call, right? So they're equivalent. Now that we have our definition here, we can now try it out. We can actually go and implement our recursion. We can actually go in and implement and try out some examples and just see how things will work. All right. So now, let's call this guy out. Divide by prime 25. You see that we got 4, 0. But if we call 21, obviously, we're going to get a remainder of 1. Okay? So, but is this... So this implements integral division, albeit not completely. Like, we are actually giving you the actual integral division. If I gave you divide div 21, 5, it's only going to give you 4. So we want to kind of match this kind of function, right? So that's a simple fix. We could just go ahead and say this is going to return just a quotient. We're not going to actually go in and implement anything else. And what this is just going to do is, this is essentially going to do exactly the same thing that we saw before, which is it follows the integral division definitions. Now, for folks who are reading the book, you might be wondering, well, why did they use a tuple? I was like, well, technically they're giving you the tuple because it is in cases where they don't divide correctly, there is a remainder. And he just wanted to show that we can totally match the API here. I'm just showing that we can totally match the API that div does to illustrate the point. But technically speaking, you are having an integer remainder that you just dropped on the floor when you do that. So you're losing some information there. Okay. Recursion itself has been seen up until now where we're basically on single inputs, single structures, structures that are more or less concrete types that aren't themselves collections, right? Can we do the same thing with collections, with recursion? Well, if you look at Learn You a Haskell, a lot of examples in Learn You a Haskell are actually based on collections. And I wanted to cover a couple of them here just to give you, a couple of examples. The first example is actually, again, these are all, working through lists and stuff, but it is indicative of how you might end up writing patterns if you're working through collections yourself. The first example is essentially finding the maximum in a list of integers, right? So how might we implement this? Well, let's first go in and define our function signature here, okay? This is from example Learn You a Haskell chapter 5. Okay. And what this function does is it will compute the maximum. I'm going to go ahead and use maximum. I don't think maximum exists, so we're going to create our own maximum called maximum prime. That itself is going to be requiring that the type variable is ordering or an ordered type. Okay. Actually, I don't need to necessarily provide the signature that way. And once we have an ordered type, we can take in a collection of those types, and we can return a variable, a result of that type. So all the types need to necessarily match, and they just need to adhere to the ordered type class. Okay. When we go and look at this, we need to again think about the base cases in our recursive case. there are technically two base cases when you're dealing with collections. The first one is obviously you've been passed an empty collection. Okay. If you're past an empty collection, you throw an error, and I'll say can't compute max of an empty list. Okay. You don't necessarily need to throw an error. I'm just doing it because, and I think the book just does it because really, if you're doing that, then you have some problems. Next is if you have, say, a single variable. All right. If you have a list of a single input, then the maximum of that single list is just going to be that, right? It's just going to be x. So we now have our base case defined. What is our recursive case going to be? Well, our recursive case is going to follow the pattern where you're going to essentially take the first value and then the rest of the x's, okay? And what we're going to do is we're going to essentially implement a guard time has a first pass. Okay. So what does this guard type look like? Okay. Well, there are two cases here. Either we have a max tail, okay, and if we're greater than the max tail, we're returning x, or, okay, otherwise, we're going to compute, otherwise it's going to be just a max tail. Well, what's the max tail? Well, the max tail itself is the recursive call. We're using a where case here that basically is allowing us to compute what max tail is. And max tail is just nothing more than maximum max of the x's. All right. Now, those of you who are looking at this, I know at first glance you're like, well, you're using max tail, but you haven't actually computed max tail. How the heck are you going to end up computing this in a non-empty list? Well, most people think that there are two cases there. One is we upfront define, if you're doing iteration, okay, in other languages, you might upfront define a max and then iterate through based on that max value, probably usually the first element. In this case, what we're doing is we're actually going all the way down to the end of the list, taking the first element, because the reason why we're going down to the end of the list is because it will hit that second base case, which is a list of single element. And then what we're using is we're going to use that as the max tail and then work our way back to actually figuring out what the max is. So that's the difference in terms of the evaluation based on what most people are familiar with when they're writing max. Okay. Now this looks all well and good, but really, there's an even clearer way to actually go and define this. If you recall, we already have a function that computes maximum, all right? And that's max, okay? Max basically takes an ordering and then gives us, given two values, gives us the max of the two values. And you can see this if you do 2 and 5, 4, it'll give you 4. If you do 4 and 2, it'll give you 4. It'll give you 5 and 3, it'll give you 5, and so forth, okay? Is there a way to leverage max in this function definition? Well, yes, there is. You can actually go ahead and use max to, instead of writing it this way, you can also write the third rule as maximum of x's as being nothing more than max of x. maximum of the x's, all right? And it's the same evaluation. It's going to end up creating the structure until it hits the base case, and then it'll recompute everything up. Okay, and we can see this here. So if we compute now maximum prime of 1, 2, 3, 4, 5, we'll see that it will compute 5 here. And it's the same if we end up using this one, right? And we end up just commenting out this guy. Okay, if we compute that, we'll end up getting the same function. Okay, in both cases, what is happening is one is just doing the straight up stricter comparison versus the other one, which is actually leveraging the function that's already available for in the prelude. The recommendation for every function just is if there's something in the prelude or in the standard library that you could leverage to build a higher order function, use it. All right. Use that building blocks instead of writing it from scratch. It just doesn't make any sense for you to write it from scratch. Okay. Another example that we could totally illustrate is implementing reverse in our recursive language. Now that we understand how structures are going to work. Again, we are destructuring the collection. And then using that destructuring to actually go and define our base case, okay, and our recursive case. So in the case of reverse, again, this is going to take any collection, and it's going to, any list, and it's going to return a list, okay? And here we have, again, two cases. Our base case is obviously the empty list, and our recursive case is going to be s's equals reverse prime x's, okay, concatenated with a list of x, okay. This seems pretty straightforward. What we just did is we just defined reverse as simple rules. And what this is doing in the evaluation is it gets a non-empty list. It says, okay, take the first element, which is 1, put that in its own list, call the recursive call. 2, put that in its own list, call the recursive call. And keep doing this until it hits 5. And then once it hits 5, it hits the empty list. The empty list triggers the concatenation. We start with the empty list. We pop in 5, we pop in 4, we pop in 3, we pop in 2, we pop in 1, and then we actually go and evaluate that at the end. All right. Compare this to writing such an algorithm in one of the other languages, and it'll become clear that pattern matching, at least for the respect of writing recursive functions, is very, very powerful. With that, I'm going to stop here and ask for questions, discuss some of those questions. Are there any questions? Okay, well, with that, there's a question that I'm not going to even begin to read out, but it's a funny question either way. I'll read it out anyway. The question is, this is sounding like recursion is a case of using endofunctors. What's the problem? Ha 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 ha. That's my first response. And if that doesn't sound like sarcastic laughing, I don't know what does. But yeah, we in general, and I didn't want to bring this up, but since endofunctors was brought up, I'm just going to mention when we're talking about Haskell or any programming language in general, we are in the class of endofunctors, right? I'm not going to say any more on that because that's us jumping ahead. But remember, the joke is we're already in the class of endofunctors, all right? Any other questions? Okie dokie. If that's the case, thanks you all for joining us. We're going on a bit of a hiatus for the next few weeks. We'll come back in August, uh, and I will put an announcement in the meetup for folks who are in the Atlanta Functional Programming meetup as to what we're going to be covering then. Until then, I hope you guys all enjoy your fourth again, and I will see you guys later. Thanks.